So welcome to the week 12 Math 24/17 review. This week, I'll go ahead and share my screen. There we go. This week we'll be talking about primarily integration by parts, and we'll also just kick it off with some practice of various integrals. And we'll go ahead and get started. Let's see, so we'll start with some integration practice. And these are, we'll go ahead and start with one example. And that is going to be the integral of 1 over 1 plus e to the x. So this integral currently doesn't fit any of our integration techniques. If we tried to make it arctangent and let u equal to e to the x over 2, well then du is 1/2 e to the x over 2. Then we don't really have a du in there anywhere. So that's probably not what it would be. If we just let u equal to 1 plus e to the x, again, same problem. We don't have our du in there. So right now we can't really solve this using u substitution. We can rewrite it in a clever way, like so, to make it integrable. Because e to the x minus e to the x is 0, so we just added 0. It didn't change our problem at all. And we can actually split up the numerator into 1 plus e to the x plus negative e to the x. And this first integral is just 1 plus e to the x over 1 plus e to the x. That simplifies the integral of 1. And that just goes to x. The second integral, we can go ahead and apply u substitution on, because now we do have that e to the x on top. So that's the integral of du over u, which is the natural log of u, so minus the natural log of e to the x plus 1. And we don't actually need absolute value bars, because e to the x plus 1 is always positive. So that is our answer, x minus natural log of e to the x minus e to the x plus 1, and then plus c. There we go. So that's just one integral. Any questions? Cool. In that case, let's go ahead and give you guys a few different practice problems. Integrals can be kind of tricky sometimes because there's usually no set way to find an integral. You just kind of have to keep trying a lot of different methods. It's not quite like taking a derivative in that case. And these are just some practice problems, so go ahead and give these ones a try. And I'll give you a couple of minutes to work through those. how's it coming? You got sine squared plus c. Cool. That is correct. The other one's coming. Struggled with everything else. Okay. Well, let's go ahead and take a look at some of these. Yeah, part A, you basically can't do it unless you know the trig identity, where cosine squared of x is equal to 1/2 times 1 plus cosine 2x. So this integral is equal to 1/2 times the integral of 1 plus cosine 2x. If you didn't know this identity, you probably wouldn't be able to do part A. But this is an integral that comes up a lot. So this is probably an important identity to know. And I'll go ahead and write that down. Cosine squared x is equal to 1/2 times 1 plus cosine 2x. Important identity. And of course, once we have integral set up in this way, it's pretty easy to just go ahead and solve. You have 1/2 x, and then plus 1/4 sine 2x. If we just use the chain rule, let's see. Because the integral of 1 is 1, the integral of cosine 2x is 1/2 sine 2x, and then we just distribute the 1/2. So that is our answer for A. Make sense? Cool. As far as part B, there are actually a few different options we have for integrating. We could, of course, just go ahead and let u equal to sine of theta. The du would be cosine theta d theta. So we would have the integral of 2u du, so that's u squared plus c, and we would get sine squared theta plus c as our answer. That's one way we could solve it. Another way we could solve it is there's another trig identity that says that 2 sine theta cosine theta is equal to sine 2 theta. So these two integrals are exactly the same. But then when we integrate sine 2 theta, we get negative 1/2 cosine 2 theta plus c. So this is actually a second possible answer for our integral. And I just thought that was pretty neat, so I figured I'd show you guys. Of course, if you had initial conditions, you would end up coming out with the same result either way. I believe in this case you would have different plus c's if you, depending on which way you integrated. Would that be the case actually? Actually, not sure about that. So yeah, maybe don't take my word for it. Look into it yourself. I just thought it was interesting how you could take this one initial problem and then integrate it in two ways to get two looking answers. If we move on to part C, Well, here we have the integral from 0 to 5 of 3x plus 2 over x squared plus 9. In this case, my reasoning for this one, when I look at a problem like this, I think, well, I could let my u be my denominator, and then I would have a 3x as the numerator. Since if I let u equal to x squared plus 9, I would have my du have some kind of x term in it. So I was thinking u substitution could take care of this portion of the numerator. But then that leaves me with this other plus 2. But then I notice, well, x squared plus 9 would also be a good denominator for arctangent. So maybe in this case, I actually want to rewrite my integral as the sum of two integrals by splitting up over the numerator. Like so. So then, what we end up with is, well, the integral from 0 to 5 of 3x over x squared plus 9. We can let u equal to x squared plus 9. Du is equal to 2x dx. So we end up with 3 halves integral du over u. That's 3 halves natural log x squared plus 9 as this left-hand integral. If we wanted to take a look at the right-hand integral, well, let's see. In this case, we're going to want to use our arctangent. So u is equal to x. A is equal to the square root of 9, so 3. And our general form for arctangent, if you remember, is we have the integral of du over a squared plus u squared equals to 1 over a arctangent of u over a. So since this 2 is just a constant, we can move it out front as a coefficient. So we have 2 times 1 over 3 arctangent of x over 3. And that would be the right-hand integral. So our answer, we would just add those two up. Of course, we do still have our limits. 3 halves natural log x squared plus 9 plus 2, I'm just going to write that as 2/3 actually, plus 2/3 arctangent of x over 3, and then from 0 to 5. Again, to get our final answer, we would just plug in our actual limits of integration. We have 3 halves natural log of 5 squared is 25 plus 9 is 34 plus 2/3 arctangent 5/3. And we would have minus 3 halves natural log 9 and plus 2/3 arctangent of 0 is 0. So this would be our final answer. That makes sense? It was a bit long and complicated, but the main point here was to split up the integral around the numerator. Cool. And lastly, we'll talk about part B. And just rewrite that down here. We have the integral of 1 plus cosine alpha over sine alpha d alpha. Okay, and this one, again, it's pretty much the same as the last, where you have to split it up around the numerator. So I'll just rewrite that like so. And if we continue to simplify, 1 over sine is cosecant. And then we would have still the integral of cosine alpha over sine alpha. The integral of cosecant is something you should ideally memorize because it's a very long and drawn out process to actually integrate. Anyway, the integral of cosecant comes out to be the negative natural log of cosecant x plus, in this case, it's alpha. So cosecant alpha plus cotangent alpha. For cosine alpha plus over sine alpha, we can use simple U substitution. And we end up with the integral of u over d, that would be du over u, apologies, which is the natural log of u. So we have plus the natural log of sine alpha, then plus c. We could go through a process of simplifying this one by combining natural logs and then probably using some kind of trig substitutions or trig identities. But I'm not going to get into that process because that's not directly related to this integral. So, all right, any questions? Cool. All right, so I guess we'll go ahead and move on now to integration by parts, which is a very powerful integration tool, and it's also pretty neat. And we'll start just by talking about where integration by parts comes from. And that actually comes from the product rule. So I'm just going to give you a brief refresher on product rule. You remember if we have two functions u and v, and we wanted to take the derivative of them, well, we could say that u prime v plus u v prime, right? You take the derivative of one, and then add the derivative of the other with the derivative of the first times the original second plus the original first times the derivative of the second. But then let's say we took this formula and we wanted to subtract u prime v from both sides. We have this formula, which is really no different from this top one. We just moved one thing over to the other side. But then from here, what if we wanted to integrate both sides? Well, then you could break apart this integral, so you'd have the integral derivative of uv minus the integral of u prime v equals to the integral of uv prime. The integral of the derivative is just the original thing. So we can rewrite it just like this. And this is our formula for integration by parts. Although you'll more frequently see it with this, with the side. So you'll see it equals to uv minus integral of u prime v. Just like this. And you'll notice we're not writing dx's because those are actually contained within these prime symbols right here. Those will have your dx right in there. So that's why they're not actually shown here. That's just a brief side. So this is where the formula for integration by parts comes from. So basically, whenever we have an integral in the form where you have two things being multiplied together, and you have a u and a dv, well, you can simply take those and find out what v would be equal to and what du would be equal to. Then you just substitute it into this formula here. So I think we'll illustrate this with an example quick. Let's say we had the integral of x times the sine of x dx. And we needed to take the integral of this. Well, it doesn't fit any of our nice u substitution rules, but we do have the product of two sections, x and sine of x. So what I'm going to do is I'm going to say, well, u can be equal to x, but then dv will be equal to the other thing, sine of x. Then du is the derivative of x, then v is the integral of dv. So the integral of sine of x is negative cosine of x. And my product rule simply tells me that the integral of x times sine x will be x times negative cosine x subtract the integral of du, so 1 times v, negative cosine x. And this du would have a dx attached, and that's it right here. Now the second integral, the integral of 1 times negative cosine x, we can pretty easily solve. So we've got negative x cosine x plus integral of cosine x dx. So our final answer is negative x cosine of x plus sine of x, and then plus c. Make sense? Cool. And of course, if we took the derivative of negative x sine x plus sine of x plus c, we would get exactly x times sine of x. A couple of other brief notes about integration by parts. You'll notice that I set up a nice little system right here where I set u and dv equal to some things. In general, first thing is you must be able to integrate dv, because if you can't integrate dv, you have no way of finding this v term. So you have to be able to integrate dv. And if possible, you want to choose u so that some derivative of u goes to 0. And what I mean by that is, let's say you had the term x squared. Well, the first derivative of x squared is 2x, the second derivative is 2, and then the third derivative is 0. So there we would hit 0. So x squared would be a good u. If we had something like e to the x, well, its derivative is just e to the x no matter what. So that wouldn't be as good of a u. But one thing to remember is this is first priority, this is second priority. So you always have to make sure you can integrate dv. And if you can choose a dv that you can integrate, then you want to look at choosing a u so that the derivative goes to 0. All right, let's see. I'll go ahead and give you guys a practice problem. Let's say you had the integral of natural log of x dx. And I'll go ahead and give you guys That is, you want d to be equal to 1. So I guess we'll ask a starting question. What should u be equal to? Not quite. Because remember, our integral should take the form integral of u dv. So we can think of it as natural log of x times, we already chose dv, so times 1 is equal to integral of u times 1. Maybe if I set it up like that, you maybe see what u should be. Natural log of x is the correct answer. But you are right, I did miss dv should technically be dx. So I guess I can correct that there. But u should be the natural log of x, like that. So why don't you guys go ahead and try solving the problem here. And I'll go ahead and give you a couple of minutes to do that. Oh, yeah, that's unfortunate. Good luck. I'll go ahead and give you the formula for integration of parts. Let's see. we got natural log of x minus 1. Well, let's go ahead and work through it and see. So in this case, minus x, okay. I believe that's, actually I am blanking on the answer right now, but let's go ahead and work through it and see what happens. So first we need to find out what du is. That's going to be 1 over x dx. And of course, v is the integral of dx, so x. And we just take all of this information we have up here and plug it into our formula. So the integral natural log of x dx is equal to u times v, x times the natural log of x, minus the integral of v times u. So 1 over x times x dx. Then 1 over x times x is just equal to 1, so we have x natural log of x minus the integral of dx. So our answer is x natural log of x minus x plus c. Make sense? A bit tricky. It does help to kind of draw everything out. Personally, I actually do enjoy drawing these lines because it's just more visual. Yeah. But there you have it. So I'm just drawing yeah. I typically enjoy doing these lines here because then it's just more visual. I can see, well, I just multiply these two together and they should be positive. And I multiply these two together and it should be negative. So I'll often do this and draw like plus signs, minus signs, just so I can see visually what things go together and what their sign should be. All right, we'll go ahead and do more practice with that. Let's see. Here we go. Go ahead and try that one out. And of course, first you should decide what your u should be and what dv should be. Just remember a couple of guidelines. dv, you have to be able to integrate it. And u, you want to choose so that its derivative goes to a constant or 0. What? you got x e to the x minus e to the x plus c. All right, let's go ahead and take a look. So in this case, we know how to integrate both x and e to the x. So we really just want to pick u so that its derivative goes to 0. Go ahead and take u for x because the first derivative is 1, so then the second derivative would be 0. Which means that our dv has to be the rest of it. Then v would just be the integral of d dx, which is just again e to dx. And du is equal to dx, derivative of x. So our answer should just be, we add this diagonal, subtract the this. Our answer should be x e to the x minus the integral e dx dx. And that leaves us with x e to the x minus e to the x. We'll see. Nice work. Okay. As a similar question, let's say we had the integral of x squared dx dx. In just a moment. So we can review those two guidelines. A couple of guidelines for picking u and dv. Your first guideline is you have to be able to integrate dv. For instance, you couldn't pick dv to be something like, I don't know, you wouldn't want to pick it to be like e to the x squared because you can't integrate e to the x squared. So you would not want to do that. That is your first priority. You have to be able to integrate dv. Your second priority is you want the derivative of u to eventually go to 0. So for instance, let's say you had x squared. The first derivative is 2x, the second derivative is 2, and the third derivative is 0. So that kind of tells you that you would prioritize making x squared equal to u over something like e to the x, because the derivative of e to the x is just e to the x no matter which derivative you take. And I guess I did just kind of give away the setup for this problem. If dv is e to the x, right, the integral of e to the x is always equal to e to the x. But I'll actually talk a bit more about this in a bit. And I'll actually get into it. You'll kind of start seeing why we choose u to go to 0 through this problem, and then we can go ahead and talk about it a bit more. So work through this problem, and then we'll talk about it. Sound good? Cool. Thank you, I was still muted. So, just a brief recap, I found du, which was 2x, and v, which was e to the x. And we know that our answer should be the product of the diagonal, so x squared e to the x, and that should be positive, minus the integral of 2x times e to the x. Of course, that should be dx as well. But then here we have, this is just another integration by parts. So, I believe what you did is you just took the answer from the previous question, which is perfectly fine. What we could also do is we could just set it up all the way again, but it would just be the same thing. We've got u equal to x and then dv equal to e to the x. But this does mean that with some problems you have to do repeated integration by parts. This would be the answer if we just copied the results of the previous problem. So, good job noticing that. But yes, sometimes you do have to do repeated integration by parts. And we'll go into a bit more into that later. It looks like a polynomial. Is that intentional? That's just kind of how it turns out. Because with a product rule, you typically have two different things being added to each other. So if you do it over and over, you're just going to be getting more and more terms added together. That's kind of why it turns out looking like a polynomial. As far as it being intentional, I don't think so, no. Yeah. To answer your question from before, if we had tried to work through this problem where we didn't make u be the term that would go to 0, if we made u equal to e to the x instead and dv equal to x squared, then du would be e to the x. v would be 1/3 x cubed. So our answer would be plus this minus this integral, so we would have 1/3 x cubed my e to the x, there we go, minus the integral of 1/3 x cubed e to the x dx. But if we kept letting u equal to e to the x and dv equal to 1/3 x cubed, or the x term, you can see that the exponent on this x would just be getting larger and larger. So we would just have to continue doing integration by parts infinitely on this term, and we would never end up actually getting our solution. That's why whenever possible, we want to let u be the term that goes to 0. Does that kind of make sense? Cool. Okay. Since we're on the topic of repeated integration by parts, let's say we had this integral. First off, how many times would you have to do integration by parts for this one? Yeah, 4 or 5. In this case, I believe it's 5. And naturally, we don't want to do that because that's not fun. It would take a while. So there's actually a shortcut method we can use, which is great news for us. And that is using a table. So think of it this way. If we had to do integration by parts once, well, then we would have u be equal to x to the 5th and dv be equal to ex. So then du, I'm actually kind of setting this up. So then du would be equal to 5x to the 4th, and v would be equal to e to the x. So our first term would be x to the 5th times e to the x minus this integral. of 5x to the fourth times e to the x. But then if we had to do that integral, we could let u be equal to 5x to the fourth and dv be equal to 8. So if this were our new u, our new du would be 20x cubed. Or in other words, you could think of it kind of this way. This one is our u, dv, du, and v for our very first integral. And we would have a second box that overlaps with it for our second integral, and so on until we no longer need to do integration by parts. So that would keep going essentially until this x term, until our u went to 0. 60x squared, 120x, 120. And then that would eventually go to 0. Are the subtractions still occurring? Yes. But luckily they take a specific pattern. So we would actually add the first one. The second one would be negative. The third one would be positive. The fourth one would be negative. So they just alternate like this. So we really easily just set up a whole system. We can essentially just write out our answer. We have x to the fifth, e to the x, subtract 5x to the fourth, e to the x, plus 20x cubed, e to the x, minus 60x squared, x, plus 120, x e to the x, minus 120, e to the x, and then just plus c at the very end, which would technically be this integral right here. The integral of 0 would just give us the plus c at the end. And that would be our answer, which is a much slower or a much faster way than doing integration by parts 5 times in a row. That kind of makes sense? Cool. And I guess I could really briefly talk about why these subtractions are, why our sign alternates. It's really because we would have the first term minus, the second term minus, the third term minus, the fourth term, and so on. But really, first we would distribute the negative sign to the b. You'd have a negative, negative, so that would change it to a positive for our second one. And negative, negative, negative would make it negative, and so on. As the subtraction signs would either cancel or not quite cancel. That's why it alternates. As far as practice, we'll go ahead and give you let's see. So yes, you would keep integrating on the dv side. Why don't you guys go ahead and try, I'll give you a, it's not too long, the integral of x cubed sine of x dx. Go ahead and try that one out. one x cubed sine x plus 3x squared cosine x minus 6x sine x plus 6 cosine x minus sine x plus c. Not quite, I don't think. Let's go through this really quick. So in this case, we want u to be x cubed because that'll go to 0. You are on the right track. Might have just gotten a bit off with your table. So if we took the derivative of u until we got 0, we'd get 3x squared, 6x, 6, and then 0. And we just integrate dv until it matches the length of u. We have negative cosine of x, negative sine of x, and cosine x, and then sine of x. Correct? Cool. So then from here, we say plus, minus, plus, minus. But then, of course, we do need to take into account the signs that are already on these. So we would have negative x cubed cosine of x, since we've got a negative attached to our cosine. Then plus 3x squared sine of x plus 6x cosine of x minus 6 sine of x, and then plus c at the end. Yeah, it looks like you were just going straight across, but it used to be going diagonally. But you were close, so just got to be careful. That would be our answer. Any questions? Cool. All right, there is one last thing that I would like to talk about. And this one I think I'm going to do as an example, because it tends to be a bit weird. What if neither of your terms goes to 0? So we don't really have a good u regardless. In this case, there's a really cool trick that you've got to use. And you can essentially first we need to decide what u and dv should be. And in this one, it really comes down to which one do you prefer to take the derivative of versus which one do you prefer to integrate. I'm going to let u be equal to sine of x because I'm more comfortable taking the derivative sine than integrating. And also e to the x is really easy to integrate. So then my first derivative of u will be cosine of x. And then I would have e to the x as well. And my second derivative would be negative sine of x. Then again, e to the x right here. You'll notice that I'm actually leaving this bottom one in the form of an integral. And I'm going to just go ahead and start writing out my answer. I would have the integral of e to the x sine of x. X is equal to e to the x sine of x minus e to the x cosine of x, and minus the integral of e to the x sine of x dx. Okay. And this is where the real neat part comes in. because the integral of e to the x sine of x and the integral of e to the x sine of x are the same term. So we can actually just add the integral of e to the x sine of x to both sides. Just like we would a variable. And like a variable, we would just say we now have 2 integral e to the x sine of x dx. And that would then be equal to e to the x sine of x minus e to the x cosine of x. And then to get our final answer, all we need to do is divide both sides by 2 to cancel this 2. So our final answer would be e to the x sine of x minus e to the x cosine x divided by 2. And of course we would need a plus c. I wrote that all sideways. Divided by 2 plus c. Any thoughts? Questions? Yeah, is that cool or what? Yeah, it's really neat. It feels like it feels almost like cheating math, but I mean, technically it works and comes out with the right answers, so it's one of the cooler things. So yeah. Let's see. You'll see this crop up occasionally. A big hint, you might have to do this trick of adding the integral back over to the other side, as if neither of your u's goes to 0. But yeah, overall, you shouldn't have to do this a ton, but it is really cool, and it will crop up occasionally, so just be careful and watch out for it. Yeah. Yeah. Huh. Interesting. Let's see. I think I'm going to go ahead and stop recording.